Okay, so recitation is about your own active participation. It means you claim your own point. At the end of the semester, we will normalize the recitation point, okay, based on the maximum. So every end of the class, please add your recitation point there in Moodle.
Okay, sir.
Okay. Okay, so let's start. Today we will discuss about introduction to optimization. Okay, before that, what did you learn last week? What did you learn last week? Last week you learned about a model, right?
Yep.
You learn about understanding behavior, prediction, and control.
Level of science.
Correct. Art and science, you learn about mathematics is one of the language, okay? One of the tool that you can use as abstract symbolic technique. And optimization is part of this. Okay, so you also learn about Occam razor. You remember? Occam razor means you want to get
Simplify.
minimum hypothesis. And if you go too much into fitting the data into your model, you will get overfitting, right? And then this is something that we don't like because overfitting basically means interpolation. What we want usually is an approximation rather than interpolation. Okay, that summarized the discussion last week. So, do you have any question about last week?
I think so far so good.
Is it clear?
Yes, sir.
Okay. So today I'll go to introduction to optimization. As you can see here, you can open the slide in Moodle. Maybe you can download it already. Did you download or did you open it so that you can follow
Yes,
the slide?
wait, let me get it.
Yeah.
The
Okay.
intro optimization or?
Yes, yes. Today is about linear programming, introduction, optimization, and then calculus-based on optimization. I don't know if this is too much for you, but let us see, okay? So this is what we will discuss. So we will discuss what is unconstrained and constrained optimization. We will discuss about standard optimization. I believe you have learned this in OR1. So basically, I just repeat what you have learned. This is my hope. But I don't know what did you learn in OR1. So I need to give an overview again, okay, in this course so that at least to make you remember. Okay. And if you did not learn, you tell me, and then we can make it deeper. Is that okay? So you need to know how to transform the objective function. You need to know how to transform the inequality constraint. And we'll discuss a little bit about convexity. Okay. So here it is. When you learn about operation in general, okay, actually the most important is not to solve the problem at hand, because that problem can be, solving the problem can be done by computer software already. So in this course, we will use Excel solver. If you want, you can also download R or Minisync or Lingo for free. MATLAB is not free. And there are many other software as well, okay, that you can use for optimization. Now, the most important aspect in learning OR, or operation research, is the ability, your ability to transform a real world problem, usually in word problem, into optimization formulation. So when you see a real world problem, then you need to transform this real world problem into mathematics of optimization formula. Now, that is your goal. After that, from the optimization formula, you input into software, okay, for example, Excel. Then you get the solution. Okay. So unlike long time ago, so there are no software, so you basically will do all the mathematics inside the software. But now we have the software already, so your problem is actually only half with this, to transform the real world problem into optimization formula. Now, when you learn any OR algorithm later, okay, the most important aspect is to know the assumption behind and the invariance, the strength and the weakness of each algorithm. And then you need to learn the general idea on how it is done. So that is what I expect from you to learn, okay? If you see, oh, I don't understand the detail of the algorithm because I cannot program it, that is fine. If I don't understand the detailed mathematics of the algorithm, probably it's fine. But if you don't know the assumption behind or the invariance, what is the strength or weakness, then it is not fine. At least you need to know why the algorithm works, why it is created. Okay, so this is what I hope you can learn in OR. Now, operation research is about optimization. Okay? There are two parts of optimization. One is called unconstrained optimization. The other one is called constrained optimization. Have you learned calculus before?
Yes, we have.
Yes, we
So
have.
you know how to do derivative, right?
Yep.
How about second derivative?
Yeah.
Oh, good. Okay, so I will share you the screen of my...
Oh, wait. By you mean second derivative, are we talking about single variable or like more than one variable in one equation?
Oh, so you know partial derivative.
We also learned that.
Good, good. Then it's enough.
Oh,
So here it is. Again, this calculus-based optimization is also in Moodle. Can you open it so that you can follow? Are you ready?
Yep.
Okay. So suppose we have function of several variables. Okay, and we want to find the extremum. So when I said extremum here is either maximum or minimum. Okay, then the procedure is as follows. First, you find the critical function point by solving simultaneous equation. You take the partial derivative to the first variable. For example, in here I have two variables, x and y. Okay, then you take the first derivative to the x, and you take the first derivative to the y, and equate it to 0. That is the first derivative. By solving this simultaneous equation, you will find the critical point where will be the extremum, which is the maximum or the minimum, maximum or the minimum. And then you take the second derivative, okay? And because you have many variables, so you need to put this second derivative into determinant. So you put it into matrix, and then you calculate the determinant. Okay. Once you calculate the determinant, then you will know, based on the determinant value, whether it is maximum or minimum or saddle point. Or if the determinant is 0, then you cannot decide whether it is maximum, minimum, or saddle point. So here is, I give you a very simple example. Suppose we have a function of two variables, x and y. Okay, 3x squared plus y squared minus x times y plus 3x plus 5y minus 8. So if we plot, you will have something like this. Of course, you see this is a single mode with only one minimum function. So we would like to find the minimum, right? So in that case, you take the first partial derivative. Okay, so if you look at this function, so you take the first derivative to x, that means you get what? 6x, and then this is y squared, so the first derivative becomes 0, right? So minus xy, the first derivative become minus y, okay? And then 3x, the first derivative become 3, the rest 0, right? So the first derivative, fx is 6x minus y plus 3 equal, and then you equate it to 0. You take the first derivative to the y, you get 2y minus x plus 5. Again, you equate it to 0. And then you solve these two equations. So to solve the equation, you use linear algebra. So you put all the numbers there into matrix. So 6 minus 1, and then 2 and minus x is minus 1. So you put it there. You put it into matrix and vector, you solve it, you get the critical point, which is minus 1 and minus 3. And then you solve the second derivative, okay? And you see the determinant here is positive, and the first fxx is 6 in this case. Then you get 6 is larger than 0. Then you know this is relative minimum point. Until here, do you have any question, or do you get it or not?
Can you please scroll up?
Scroll up, okay.
No, not that much. To the point where we have the inverse of the matrix.
Inverse of the matrix, okay.
Yeah, this is the method that we use to find the x and y.
Correct. So if you have, I will give you a screen whiteboard. Okay, so if you have a times x equal b, right? So how
Yes.
do you solve x? So x a times a inverse, okay, equal a inverse, sorry, a inverse times b, right?
Yeah.
A inverse times a is I, correct? So basically,
Yeah.
Yes.
Identity
so,
matrix. Yeah.
correct. So minus 1p. This is how you solve it, right?
Yeah.
Mm-hmm.
Okay, that's exactly the one in the, where is that? Yeah, here. So this is exactly this. You see, this is the factor x is xy equal to a inverse times b.
How do we get inverse again? I
Oh,
forgot. Like the
uh, yes,
one over
linear
determinant
algebra.
times.
So you get the inverse by getting the determinant in this case, or
Yeah, like one over determinant times.
that is for 2 by 2. In general, for getting inverse, you use Gauss-Jordan or LU decomposition. Okay, if you are not sure about linear algebra part, I have, you go to Revoledu and then find linear algebra. There are calculator there that I made that you can also.
Oh, okay.
Okay, so you type in Google Revoledu linear algebra. Okay. And you can also find Revoledu matrix inverse. There are calculator there that you can use. Anyway, your exam is always open book, open online, so open everything, so you don't need to worry. And if you work in the real world, you always have your all tools available for you anyway, right? So in
To
first,
be honest, during the calculus class, I always use the calculator online
yes, yes,
calculator.
yes, you can use calculator. So uh, in linear algebra, you need to use, say for example, you can use Gauss-Jordan using RREF. I have the, let me put in the chat. Where is the chat? Here it is. So for everyone, okay, I put in the chat the link to go to Revoledu. Okay, I will share that so that you can see. Here it is. So this one in Revoledu, finding inverse using RREF. Okay, so this is it. This is to find the inverse matrix using Gauss-Jordan. So in here you have you just put the matrix here. Okay, for example, I have 6 minus 1, minus 1 and 2. So I will put there 6 comma minus 1 and then minus 1 comma 2, right? And then I will find the matrix inverse there. So this is the calculator on how to calculate matrix inverse. And finally, you get the result.
If only in Operation Research 1, Eugene, we knew about this.
Now you know.
So you only need to type what? Can I see what you just typed?
Yeah, I just typed the 6 minus 1 minus 1, 2. You need to put the semicolon at the end because the program needs to know.
Ooh.
Very
Okay.
easy. You see? Super easy, right?
Okay. Thank you.
Okay, so I have here you have the matrix A, which is 6 minus 1 minus 1, 2, right? So then you input that. At the end, this is how they calculate manually. You can see how you calculate manually also in this calculator, in Revoledo. And then at the end, you get the matrix inverse. Right. And then matrix multiplication is clear, right? So you can just multiply the matrix. So up to here, is there any question? So if you think this is a little bit difficult, you tell me, okay? I don't want to drag you into something that you don't know. So what do you think?
For me, I think a little bit difficult.
Eh?
For me, I think a little bit difficult.
Oh, okay, so which part is difficult so that I can try to explain to you?
Maybe I have to learn first from your tutorial.
Okay,
So
you
if
can
I have
learn.
question, I will ask you.
Okay, no problem. So the formula here is okay, right? The first derivative is okay, second derivative is okay. You are familiar with this, right?
Yes.
So the symbol, the symbol is no problem with you.
Yeah, but
Okay,
maybe the systematic, I still don't get it.
okay, you don't get it. Which part? Okay, let's start. Maybe I'm too fast. Let's make it slow. Okay. Okay, the function here, do you get it or not? The one that I put with the zoom.
Yeah.
Okay, the function here, do you get it or not? That function is actually this shape.
Maybe.
Maybe, or you can type, you can use any software,
Okay.
MATLAB, or maybe in the internet there is some software. I use MATLAB for this, but you can try to use any software to draw it. Okay, but
Okay.
it's not really important because sometimes if you have so big system, you cannot draw anyway. Anyway, this is the system that we have, say equation of fx comma y, 3x squared, y squared, and so on. What do you think about this equation? This equation is quadratic formula, right? Do you know?
Yeah.
Okay, I think you learned quadratic formula in high school, isn't it?
Yes.
Okay, good. So next, we want to find the minimum. So first take the first derivative. So question to you first. Do you know how to take the first derivative? Do you know how to get from this function to the first derivative?
I eliminate the x or y.
This is simple. You see, 3x squared. If you have 3x squared and then you take the first derivative to the x, what is the value?
6x.
Okay, I will type. Okay, I will type here in the. Okay, I will erase everything. You forget the calculus.
Yeah.
Okay. So you have, say for example, admit. Okay. Let me cut. So y, what happened? So y equal to x squared. Okay. Okay, 3x squared. So what is dy dx equal? You know? Anyone?
6x.
Correct, correct. 6x. Oh, very good. So now I will make it more difficult. What is the next one? Okay, now you have f 3x. Now I will make it more difficult a little bit. So I will delete this. Okay. So now you have two variables. Okay. So fx comma y equal to 3x squared. What is that? The next term? Plus 2 squared, right? Plus 2y squared. No, now tell me what is the del f del x?
6x.
6x, correct. Okay, this one still 6x. Tell me del f del y.
4y.
Very good. Okay, 4y. So you know the partial derivative. Wow, super. So I have no worry in that case, right? So you can, so now you have the first derivative here, you have no problem, right? Supposed to be. Where is the screen again? So this first derivative here, no problem.
Maybe.
Still maybe. Which one is the one that's not clear?
For me, it's okay, but maybe for the second derivative, I a little bit confused.
Okay, so no, before the second derivative. Now, from the first derivative, do you know how to get into matrix?
Maybe you can explain it.
Okay, I will explain. So, if you have 6x minus y plus 3 equals 0, right? That's what you have. And then 2y minus x plus 5 equals 0, right? So then you want to put this into matrix. So then what is the matrix? The matrix is A times x equal B. Okay? So then you need to put matrix is A. X is in this case xy. Correct? So, and then B is minus 3 minus 5. So then the A, matrix A will be 6 minus 1. And then in the second equation there, remember the y is 3 first, so you need to put x first. In that case, minus 1 and then plus 2. Because in matrix multiplication, every row multiplied by every column. Up to here, do you have question?
No.
So is it clear? Really clear?
Yeah.
Good. So you know how to calculate. Then calculation of x is simple. Just take matrix inverse, multiply by that, then you get this value. Okay. So you get the critical point of AB is minus 1 minus 3. So now take the second derivative. To get the second derivative test, okay, remember in the second derivative test, the test is this value, which is if fxx times fyy minus fxy square. From where this come from? This come from determinant. So, meaning you need to put the second derivative xx, xy, yx, yy into a matrix, and then you get the determinant, you will get the second derivative test. Okay, so then what happened is, so fxx, how do you get the fxx? From the fx, you get again, you take the first derivative of fx. Remember, fx is 6x minus y plus 3 equals 0, right? So you take the first derivative of 6x minus y plus 3, 2x. What is the value?
6.
Correct. So that is the one that put there, 6. And then fyy. Fyy mean fy, the first derivative a while ago, which is 2y minus x plus 5. Then you take it into, take the derivative 2y. So 2y minus x plus 5. Take derivative 2y. The result is?
2.
2. Very good. So there, you get that. Now, fxy, meaning either you get the fx or you get the fy, and then take derivative to the next variable. So say you take the fx, and then you take it into the first derivative to the y. You get?
-1.
Correct. So then you square that. Okay. Then you get positive 13, which is larger than 0. Right? So then you have everything. And you put that numbers into the function again, you get minus 17. So you get the value of minimum at -1, -3, which is minus 17. Up to here, is it clear? Do you have any question? So
I think it's clear.
it's clear, okay? So this is an example that you learn in calculus. Okay, this is not new, this is not really OR yet. So this is just unconstrained optimization. So you see the function you have, there is no constraint at all. Okay. So, okay. Now let's go back to the slide. I will share you with the slide, intro optimization. Okay, here it is. So in unconstrained optimization, okay, you want to find x in here is a vector, to maximize or to minimize the objective function fx. Okay. Always like that. So unconstrained optimization is basically you want to find decision variables x to maximize or to minimize fx. Okay. So the next one, okay, the same thing here. So this is unconstrained. What is unconstrained optimization? Is a special class of optimization that has no constraint at all. It has only objective function. Okay, so here is another equation that you can minimize, and then you can try to solve it in Excel.
Sir,
Yes.
I want to ask about
Please.
this unconstrained optimization.
Yes.
Like, do you have any real life example about that? I mean, like one equation that needs optimization but don't have any constraint at all.
Yeah, this
Does
one.
it exist?
This is exactly the same. This is exactly the example. The example is minimize this equation minus 1 minus x squared plus 100 y minus x squared squared. You
I
want,
mean, like how? No. I mean, like how is that applied in job, like in real life? Something
in
that
real life.
we
In
want to
real life,
minimize,
oh,
but we don't have any constraints for that.
okay. In real life, you always do any decision, correct?
Okay.
And all your life is actually based on optimization. The fact that you are sitting in this class is actually optimization. You are eating lunch is also optimization. You give any example of things that you decide. In your decision, you think in terms of variables. Okay? And then you want to maximize or minimize. You maximize, for example, in real life, if you are talking about business, okay, then you want to maximize your profit, correct?
Yes.
To minimize your costs.
Yes.
So if you are talking about personal life, you want to maximize your gain, okay, or your love life, for example, or you want to minimize your time, correct?
Yes.
Okay, so all of this in daily life, you think about something that you want to optimize. What do you want to put into maximum? What do you want to put into minimum?
Yeah. Okay.
So now I'm putting this, once you have your problem at hand, that is why you have you have group project, you know. In the group project, you get the case study that you want, a little bit bigger, and then you try to make the equation, okay, the objective function. Okay, and then you try to create the constraint there, and then you find the solution. Okay, that is the task in one semester to do just one optimization. But in real life, you do so much optimization. Actually, everything that you want to do to maximize or to minimize something, that is optimization. Okay. By saying that, oh, I want to do unconstrained optimization, that means you don't put any limit. You don't put any limit to the decision variable that you have. Say you want to have maximum profit, right? But you have no constraint at all, meaning that you have so much money, you have so much time, you have so much worker. Okay, that means unconstrained. Is that clear, or you have any other question?
Yes,
Oh,
it's clear.
Good. So, of course, the equation in this course is rather simple. You see, I just put a quadratic equation. In your case study, should be much complicated than that, right? In your group project. So, let's try to solve this simple quadratic equation, only one variable. Can you find x that maximize 2x minus x squared plus 1? Can you do it?
Would you mind to show the question?
It's in the slide. Oh, the screen. Okay. Okay. Yeah. Can you solve this?
Should be able to. Yeah.
Yeah, now, can you take paper and pen and then you solve this now? Practice.
X equals to 1.
How do
Hello?
you get it? Hello, how do you get it?
By just doing the first derivative.
Correct. Very good. So to take the first derivative, you get x equal to 1, and then that is
Put it equal to 0, and you get the result.
correct. Okay, very good. So you have no problem at all. It's the unconstrained equation, right? So the second derivative is to determine whether it is maximum or minimum or saddle point. Okay, the first derivative is to get the actual x or y, the actual domain value. Clear? Any question about this?
No.
Good. Okay. Now, general optimization model. Okay. A while ago, I gave you unconstrained. Unconstrained optimization was developed probably 17th centuries. Okay, by Newton, Leibniz, and so on. But later on, they found out that, look, real world problem is not unconstrained. Real world is always have constraint, isn't it? Always have some limitation. You said you want to maximize the profit under certain resources. You always have some constraint that the capital is limited, the number of people you have is limited, right? The time is limited, and so on. So that limit represents the constraint. Okay. Now, if you want to put optimization model, okay, optimization formula, you always put something like this. Find x is the decision variable, to maximize or minimize the objective function fx, okay, subject to constraint, okay, have three constraints here. One is the equality constraint, so hj of the x equals 0. And the second is inequality constraint, gi of the x is less than or larger than 0. Okay. And then you have boundary constraint, but about its x, okay, must be between lower boundary to the upper boundary. So this is general optimization model. This is what you need to put from the real world problem into mathematical formula. Okay. Once you can create this optimization model, then you can input this model into Excel or into Minisync or into MATLAB. Then the software will solve it. The software cannot solve the real world problem. It is you who transform real world problem into this general optimization model. Is it clear? Are you still there?
Yes, sir.
Yeah.
Okay. So now from the general optimization model, okay, you need to have what is called standard optimization model. What is standard optimization model? You see here, the same as before general optimization, you find the factor decision variable X. When we say standard, we don't minimize, we only maximize. So you maximize the objective function fx subject to, okay, now look at the standard here. The standard here, the inequality constraint is always less than 0. The GI is always less than 0. Of course, the HJ here is always equal. The equality constraint still okay, the same. The boundary constraint is still the same. But the inequality constraint is different. Compare this. You see, the inequality constraint in general optimization, you can either have GI is less than 0 or GI larger than 0. But in standard, you always have GI less than 0. Is it clear? Can you find the difference between general optimization and standard optimization? Tell me. Anyone?
I don't know. How?
Don't know? What is the difference between general optimization and standard optimization? Can you compare the two slides? Anyone?
I don't know.
You don't know?
Which slide? Which slide?
Standard is only for maximize, while general can find the maximize and minimize.
Very good, Lilian. Next, what is the next? There are two differences, okay? Standard is always maximize, not minimize. Standard is also always what? Check the constraint.
Larger than 0.
Less
Correct.
than 0.
The GI is always less than 0. In general, the GI can be larger or less than. Okay? So there are two differences between standard optimization and general optimization. The first, okay, in standard optimization, always maximize, not minimize. Second, okay, in standard optimization, the GI is always less than. Anyone get it?
Yes, sir.
Okay, very good. Okay.
I say that the standard optimization is larger than 0.
Which one is larger?
The standard optimization.
No, the standard optimization is less than 0. The GI is always less than 0, not larger.
Say it's vice versa before.
Eh?
I say when you ask to me, I said
Yeah.
that the standard optimization is larger than 0, not less than 0.
Ah, okay. Should be less than, okay?
Thank you, sir.
Yes. So, why? Nonsense. Where am I? Introduction to OMS. Standard optimization. Where is it? Introduction to optimization. Okay. So now we have the standard optimization. So let's interpret that. So you see here that when we said optimization, okay, is basically you want to have relation between decision X to allocate some resources. Okay. Now the decision variable with this X there represent the activities that use some resources. Now there are many alternative ways to use the resources, right? Now its activities will produce some return. That return will contribute to the objective function. Okay. Now, the constraint would represent the limited quantity of your resources. Now, having the standard, okay, having the standard optimization model, now you will ask, I only have maximization. How about if I want to minimize, right? I only have inequality constraint that is less than 0. How about if I want to have inequality that is larger than 0? So, actually, rather simple. Okay, when you say I want to minimize, that means you take the maximization of fx is actually equal to the minimization of the minus fx. The same thing, any inequality that gi of x is less than 0, this is equivalent to minus gi larger than 0. Right? Simply by taking the negative value, you can take the transformation. Until here, any question? So,
No,
yes, please.
no question, sir.
No question? Okay. So, say if I want to, I ask you, can you minimize this value? Okay. But remember, your standard is maximize. Then you take the negative of the minimization to get the maximum objective function. Is that clear?
Yeah.
Okay. Now, for the inequality, I think you learned this also in OR1, right? When you do a linear programming. You remember slack variable, surplus variable in linear programming? Did you learn it? In OR1, did you learn slack variable, surplus variable?
I remember a little bit of slack variable, but I haven't heard of surplus variable.
Okay, okay. Now, suppose you have inequalities, okay, that is GK is less than BK. Now, you want to transform the inequality constraint into equality constraint. Okay. Now, if your inequality is less than, then you have what is called slack variable. So, say you have GK less than BK, then you create a new one called XK. Okay, this XK is called slack variable. So you add GK plus XK equal to BK. By adding slack variable, that is equivalent to you transform the inequality constraint GK less than BK into equality constraint. Do you get it? Maybe what you want to ask is, why should I transform the inequality into equality, right?
Yeah.
Yes. So the problem happened because when you do mathematics, okay, linear algebra, you cannot have inequality constraint. What you have is only A times X equal B, isn't it, in linear algebra?
Yes.
Right. A times X equal B, that's what you have. So there is no less than or larger than. So if you want to put your problem into mathematics, okay, of linear algebra, then you need to transform the inequality constraint, whether it is larger or smaller, into equality constraint. How to transform is to add slack variable or to add surplus variable. When you will get the surplus variable, you will add surplus variable when you have inequality constraint of larger. GK larger than BK. Okay? When you have inequality constraint of GK larger than BK, then you transform this into equality constraint by subtracting non-negative surplus variable. So you have GK minus XK equal to BK. Do you get it? So again, why do you need slack variable and surplus variable? Tell me.
Transform inequal constraints to equal.
Yes, transform it in.
So that we can operate the constant equation.
Correct, correct. So now the question again, is slack variable transform larger than or less than?
Less than.
Very good. Surplus variable represent transformation of larger than or less than?
Larger than.
Larger
Very
than.
good. That is the question in the exam. Okay, very simple, right? But at least you get the understanding. If you don't understand, you don't know. Correct? So this is an example. Okay. So you want to convert this 5x1 plus 6x2 less than 20. Right? So remember, this is less than. If you want to transform this, what is this? You need to add what variable?
Variable.
Slack variable. Okay. So let's take the slack variable S1 or similar to X3 in this case, right? So how to get the S1 is equal to 20 minus 5x1 minus 6x2, right? So in that case, S1, so the original inequality a while ago and on the top will become equality. So now you have 5x1 plus 6x2 plus S1 equal 20. You see, now you transform inequality become equality. Of course, you always put the auxiliary non-negativeness condition that S1 is always larger than or equal to 0. Okay, so this is slack variable. Until here, do you have question? Clear slack variable?
I think no. It's clear.
No question. Okay, so remember this is the general linear programming. Okay, you want to have maximize fx, okay, where the fx is actually a simple alpha times x, right? This is just a linear combination subject to what? Subject to constraint of a times x equal b. Hey, you look at this. Subject to ax equal b. There is no inequality here, except that the boundary condition, all x must be larger than 0, isn't it? So this is why Okay, you see a while ago, this is why you have slack variable. This is why you have surplus variable. So the X in this subject 2 must be containing the slack variables and the surplus variable. Is that clear or not? When you have a problem, okay, first problem will be inequality, right? But when you want to put it into a linear programming problem, you need to put it all into equality only, no inequality, which is A times X equal B. Until here, any question? Any question? Really? No question at all?
I'm confused that I don't know what to ask.
Okay, you don't know what to ask. Okay.
Slide.
So I will stop for a while, and then before I'm going to the linear programming again, so let's go into your presentation. Is it okay? Or you want to take a break first before we go to your presentation?
Take a break first.
Okay, 5-minute breaks. Now my time is 10:40, which is your time is 9:40, is it?
Yeah.
Okay, so 9:45 in your time. Come back, okay? Anyone want to continue with the, let's go to the next presentation, if not.
Okay.
Okay, thank you.
Okay, thank you.
Thank you, okay.
Okay.
And everyone please create this group, Powerpuff Boy.
Where do we grade it again?
Revol 2, Revol 2.
In
Revolution.
the model. Okay. So next group. Next group.
I guess it's me and Lillian, the Bright Knights.
Yes, yes, please. Right night. Okay.
So okay. Hello, Lillian, are you there? Where's my
Yes, I'm here.
teammate? So me and Lillian decided to choose a problem about what is it called, a route inspection problem, like the Chinese postman.
Okay.
Yeah, it's somewhat similar to Abel, I guess, but either we have two options. We don't know which one we're going to use, but the Chinese postman one is like we want to minimize the delivery time for couriers in Surabaya.
Okay.
We want to optimize. We want to find the best routes for couriers to to deliver their products, because nowadays during the pandemic, everyone is depending on couriers, and maybe we want to look at it like we can also try to map out which routes that have less traffics during rush hour, and so on and so on. That's our approach. That's for the first option. Then the second option, the alternative for that problem is I remember that you explained about decision making.
Mhm.
We want to optimize the decision making in supermarket, where the aisle, the what is it called? How you uh, how you uh, the what is it called, Lilian? Hello, Lilian, help me, guys.
What what?
Placement.
The mapping out of the aisle in the mapping
Yeah,
of
like
aisle
the
in
fishbone
supermarket.
diagrams or something.
So which one you put at the entrance, near the entrance? What stuff do you put in the each part of the supermarket? I guess that's what we are trying to do.
I don't get clear idea. Can you explain, Lilian? What does mapping mean?
Okay, for the supermarket. So
Mhm.
in supermarket there are a lot of aisles, and
Okay.
we like the placement of the product. Like the first aisle is vegetable, or the second aisle is meat, sort of like that.
Oh. And then, what is the goal?
The goal is like the efficiency, like helping the customer reach the product that they wanted, and they can find it easily.
Oh.
Like probably how to for example, the order of the aisle can be ordered as such that customers might get what they actually don't need, but because they saw it, then they buy it. So hence more profit to the supermarket. Is
Okay.
that possible in decision? Because since I have never learned about the decision making thing, but that does came to our mind.
Okay. I do have paper on that long time ago in 2009, I think.
Okay, so
Fine. I forgot already. Okay. I think I have a paper. Oh, in 2009, I have paper with, I think, oh, here it is, in East. So check my publication. I give you the link there. Number 53. Pedestrian static trajectory analysis of hypermarket. So I can share some screen to you. But this is the paper. So in here we have finding the, so this is in Surabaya, in hypermarket, I think in Hypermart, and they use questionnaires. This is one of my students in civil engineering before. And then we track them, and then we calculate using a network, and then we can get what is the walking distance and so on. So we find the shortest path in this case. And finally, you can get the actual distribution of each of them. And at the same time, this is the final result here, is calculating the flow. So then you will see which alley actually being used and which alley is not used. And it's actually interesting there that you see the number of people in the bakery, and of course along the main route will be the maximum. But the one that is not seen with is, for example, the furniture, the bed cover, people, it's not really a bicycle, for example. Not really many people will go there. That means we practically will see if we rearrange this as an optimization, so you can continue this study, that will be something new that we can find which arrangement is actually produce the best profit for this supermarket and so on. I don't know if this is something that you want. What do you think?
I guess that's, if, I mean, you have already have a paper on that.
No, you can continue that, or you can create something new. I don't know.
I don't know. But I
No,
think
at least the idea you can get. So
yeah, I see. So Lillian, which one do you think is? But by your own opinion about our first idea, the routes for couriers in Surabaya,
that is also good. Yeah.
do you think that's applicable? Like, do you think that's going to be like? Is it going to be too hard? Because I don't really have any experience like in like.
What I can suggest is if you have some, business, maybe your parent, then you want to help them, then you solve their problem. That will be real world problem that you can solve, and you involve with your parents' business, helping them. So that will be the best way, because you will be motivated more rather than just problem that you don't really use in your life, right?
Well,
so then you can get data also.
I see. Okay. All right.
So try to propose something that you can get the data and you can also use it in your life. Okay, something that will motivate you. So
Okay.
if you do something just for the class, that will not motivate you enough, correct?
Yeah, I guess so.
Any difficulty will make you down. But if you think something that will benefit you in the future or benefit your family, okay, that will motivate you. That is more reasonable to do. No matter how hard it is, you will do it.
Yes, sir. Correct.
So try to propose something that will motivate you.
Okay. I see.
I have an idea for you.
Please, yes.
So you know how bad, well, you don't know how bad the bus routes in Surabaya are. So why don't you devise a way that like optimize it so that it'll be similar to, advanced countries,
Oh,
Surabaya,
you mean the Surabaya bus that you always ride on?
yes.
I
So
see.
So right now, in order to get on a bus, you usually have to wait an hour and a half for a bus to
Really?
come.
That
Yes,
bad?
it's that bad. And the
Really?
routes are
Okay,
unacceptable.
imagine that I have power, okay, to create a new bus in Surabaya. Where should be the route?
From mall to mall?
Yes, okay, but you need to check where is to get the demand enough to make a profit. Okay, right now, the 1.5 hours is because there is no demand and they give for free, practically just subsidies by local government, right? So this is not sustainable. Think that in the long term, government will think that, oh, I have no more money, so I will stop this service. But if the service is profitable, more people will join, then more people will be served. So think about what is the route, what is the marketing, in terms of the marketing business, that it will actually create profit.
I guess we can find like routes where they have like office buildings. Like usually they are
Yes.
located in one area of the city, right?
Right. So I do have, again, if you want to do bus, I did some very simple tutorial long time ago. Again, I was in Japan. I forget the name. Is that sensitivity analysis? No. I did bus analysis when I was in Japan.
I see. Okay.
So you can search in my tutorial. I think I have, oh, this one. Yes, okay. So I'll give you the link here in the chat. Feasibility study. This is about bus.
I see. Okay.
Okay.
Thank you.
This is the cost benefit analysis, but this is not optimization yet. But you can easily change this into optimization. So all the formulas is there, so you can also use. So in this case, we want to know how many buses, right? Of course,
Yeah.
something, okay? You assume how many people, how many buses, and you need to put the headway there, meaning between bus, how many minutes people should wait. Then how many buses. And from there you get the route, right? Because you know the distance and you can assume the speed.
I see. Okay. I guess that's can we use that idea? Even though that
That's fine.
thank you, Abel, for your idea. I guess that helped a lot.
Yeah, you discuss first among your group and then you can propose again.
Okay, we will get back to you with our final decision which project we will do.
Right.
So we have 3 options. Thank you.
Thank you. Next one, who's next? I think one more group, right? Is that Darin?
My group, sir.
Yes.
Yes. I will show you.
Darin's group name is Holistic.
Yeah.
Okay. So please.
Can you see my screen?
Check. Yes. Okay.
Okay. I want to introduce my group name is Lisnik, and my name is Darin, and I'm group with Stephen Gunawan. And my group project is how to collaborate art versus science. In this, my case study is like when you have factory and you worker in there, and you force them in one day you have to product 1,000 pieces, but at the real life it's only can product 500. I want to maximize it because I think the people can do that if they have like the efficient or the effective way to make the something like that. But in the real life, there's something like they have to get rest, they have to pray, they have to do something else. Well, in Indonesia, I think, like if in the China, I think they have some effective and efficient way so the people can work hard and they can achieve the goals. I think that my case study.
This is still very general, Darin. Can you make it more specific?
I think my mom worked in the shoes factory. And I want to...
Shoes factory?
What, sir?
What
shoes
kind
factory.
of shoes factory? Okay. Shoes factory, and then?
Yeah. I want to like the worker can maximize their potential.
Maximize, what do you mean by potential?
Yeah. They can achieve 1,000 pieces of shoes in one day.
Okay, production. You mean production?
Yeah, the production. But in the reality, they still only can produce 500 shoes a day.
Okay.
So it's not good for the company, I think.
Okay.
Like the input and the output is different. That's why the price of the shoes cannot be.
So you will increase price.
Bersaing.
Yeah, it's not competitive enough. So you
competitive.
The price, you want to include labor, time, and utility. Is that the? No, I'm trying to guess what will be the decision variable that you will put.
Yeah, I mean like that.
Okay. So, do you think you can get the data for this? Do you have connection to the shoes factory?
I will do what I can. If the boss not allow me, yeah, I will try another project.
Okay.
But so far, I have the connection, sir. So I think it will be okay.
Okay, good.
So,
So,
yeah.
meaning this is a real world problem that you want to solve within your capability, right?
Yes.
Yes, sir.
Okay. So any other group members or other participant want to ask this group project? Nyoto, you want to ask Darin? Lilian?
I guess not yet.
Oh, I don't quite understand what.
Okay, Lilian don't understand, so please, Darin and Stephen, please explain again.
Okay, so like this, Lee. So if there's a worker that they have a target like, okay, per 1 week you have to finish 1,000 shoes, but in reality, they only can finish like estimatedly 500 shoes. So it is not efficient, right? So we want to make it more efficient.
Oh, okay.
So wait. So what's the point with the how to calibrate art versus science? Is that motion time study, right? Like we used to learn like with Miss Deborah, right? What you mentioned.
Yes. Yeah, the
Like
ergonomic.
motion time study.
Yeah,
Oh,
motion
so
time
what's
study,
the
ergonomic.
what's the maksudnya how to calibrate art versus science? Maksudnya apa? I don't quite
Yeah,
understand
I
that
mean
part.
like if the businessman think they want to achieve more product, but at the reality, people have limit. They have to take a rest. They still have to go somewhere else, and they cannot achieve what the boss want like that.
No, no. I think what Ronnie meant is why you say calibrate art versus science. What art got to do in this project of yours?
Art is abstract,
Yeah.
and the science is logic, right? And I want to like connect it, like find the good and try to
Yeah, that's what Mr. Kardi explained to us yesterday.
Yeah.
But what's the connection between the maximizing time and art?
Yeah, maybe I want to maximize both.
Okay. Yeah.
Okay. Do you think you can finish it on time?
I will do my best.
Okay,
Do you
everyone.
have any suggestions, sir?
Please give your review on each group. Okay, so we have 3 groups here: Powerpuff Boy, Bright Knight, and Holistic. So you give your grade 0 to 100. Okay, 0 is bad, 100 is the best, and then tell why you give that grade. Don't worry, your grading is aggregated, so you don't need to worry about someone will know that you grade them. I will aggregate, meaning I will take average.
Okay, sir.
Okay. You submitted in Moodle, right?
Not in Revoledo.
Yeah, in Moodle Revoledo.
Oh, okay. I will stop share, yeah, sir.
Yes. So while you put that grading, okay, so we will break for 5 minutes. Is it okay?
Yeah.
Yes, sir.
It's exactly 1 hour. So 11 in your time is 10. 10:27, so 10:32.
Okay.
Okay.
So see you again 10:32. Okay, are you there?
Yes, sir.
Everyone back? Is everyone
I'm
back?
here.
Yeah.
Okay. Okay,
Yes, sir.
let's start again. Okay, so we've got, okay, for the next presentation, when is that? Next presentation, I think in April, is it? Or March? In the course syllabus. Okay, March 2. Next presentation will be in March 2. Please demonstrate the prototype of application, and you need to put your mathematical model optimization formula, okay, and how you will calculate probably some algorithm that you want to put. Okay.
Okay.
So you will also create a PowerPoint presentation. Okay. So be ready for that project presentation, okay? Now let's continue with the lecture. Okay. So did I share? Can you see the screen that I'm sharing? No.
Right now, no.
No. Okay. Here it is.
Now, yeah.
Yes.
Okay. So if you look at this classification of optimization, okay, so you can see you have general problems, okay, and in optimization you can have a single objective or multiple objective. In this class we only have a single objective. Now, based on single objective or multiple objective, you can have unconstrained or constrained optimization, right? And then now, depending on the variables that you use, you can have either continuous, meaning real number, or integer, okay? Or you can have mix between real and integer. Then in the level 5 function classification, now depending on the function that you use, usually in the objective function, whether it is linear or non-linear, in the constraint equation, whether it is convex or non-convex, whether it is differentiable or not. Okay, so now optimization itself, so this is the same thing, but this one is used in the rather than in the a tree. Now we have a different way of looking at it. Okay, whether a single objective or multi-objective, whether it's unconstrained or constrained. Now, whether it is unimodal or convex or multimodal, and so on. Okay. Now, if you look at this, what you will learn in this course is only a very small part of optimization. Okay. We will not deal with everything here, but at least I want to touch certain part of this. Now, certain optimization algorithm, okay, usually can be done by either deterministic or stochastic. In deterministic, you have learned linear programming, okay? And in this course, we will learn nonlinear programming. And there are also many ways to do deterministic approach of algorithm for optimization. In stochastic, you have a heuristic approach or meta-heuristic, either trajectory-based or population-based. For example, have you ever heard about genetic algorithm? GA. Did you heard about it?
I don't.
You don't know. Okay. So GA or genetic algorithm is also one of the technique of optimization based on stochastic meta-heuristic population-based. Right. So there is also, for example, uncolony algorithm. That is a stochastic meta-heuristic trajectory-based. So these are the classification of algorithm for general optimization. Now, in this screen about local and global optima, so we have X represent the input and Fx there in the vertical represent the output. Okay. Now, the drawing here is only one variable, which is F is a function of X. Then you can see there are local minimum and local maximum, okay, local and global maximum there. Can you understand the meaning of local maximum and global maximum? Global maximum mean within the range, that is the maximum. Local minimum mean, local maximum mean within the range, when you drop a ball there, okay, it will stick to that line, the curve there. That means it will stick to, it will go searching the local maximum. Okay, I will share the screen so that you will understand. Okay, I will delete this. How to get, okay, all drawings. Okay, suppose you have a curve like this. Okay, then in the optimization, you start with certain point. For example, you drop in here. Okay, so this is the point that you drop. And then it will search. For example, you use gradient. Okay, gradient mean you will find the tangent of that line near the one that you drop. Say you want to search the maximum point. Then based on this drop, okay, you will go into this point, the one in pink. Can you see it? And then the one in pink, again, you will search the gradient in this particular place. And then again, you will move up to this point, the next one. Yeah, I will put it in purple. So when you go to this purple line, okay, and you get the gradient here, this is already straight line. Okay, that means this is already reached the maximum. So your algorithm will stop there, and you will get the result of your algorithm. This is called local maximum. Did you get it? So when you get the local maximum, the algorithm stop and then give you the result, okay, and say that this is the optimum value. But is it true that this is the optimum value? Well, yes, it is optimum in terms of local maximum. Okay, but within this range, actually the global maximum is not there, isn't it? The global,
It's on the right.
yes, on the right in here, right?
Yes.
Okay, but the algorithm will not be able to find that. You know why? Because the gradient will go down in this valley, isn't it?
Mm-hmm.
So it will not go up. So it means the algorithm will be trapped. Okay, will be trapped in the local optima. Any optimization algorithm will always have like that.
Mm.
Did you get it? Any. So that's why we have what is called unimodal and multimodal, isn't it? When you say unimodal, meaning you only have one peak or one valley. Okay, so unimodal is something like this or something like this. Okay, so only one peak, only one valley. So, but if you have many peak and many valley, that means if you have multimodal. So real life problem usually multimodal, right? Then you may not get the actual maximum or the actual minimum. You will only get the local maximum and local minimum. So then you ask how to solve this problem. Then you probably want to randomly drop your initial value into here, into here, into here, right? Into here. So you will randomly drop anywhere in your domain so that hopefully you will eventually get the global optimum. That's why when you see the algorithm, sometimes you use Excel or you use MATLAB or you use R, your result, when you change the initial value, it will give you different result. Why? Because your algorithm was trapped in the local optimum. You got it or not? Dealing with the algorithm, so in that case, how you will solve it, you drop different initial value randomly. Okay? So come back here. So you know, when you have multimodal like this, okay, you can get the global maximum only by randomization. Okay, but when you run only one time, one initial value, it will give you only local maximum. Okay, so that's why you need to do, sometimes you need to do sensitivity analysis. You want to know, oh, am I actually in the real local maximum or in the actual global maximum? Okay. You want to know what will happen if I change the X slightly to the left, slightly to the right. Okay, that is the meaning of sensitivity analysis. Next, in your classification a while ago, you see the landscape is either unimodal or multimodal. Unimodal there is called convex. Okay, so what is the meaning of convex? So mathematically speaking, okay, a set S of a real number of n dimension is a real vector space. It's called a convex set if this formula happen. Okay, if you put any value of t times x and plus of 1 minus t times y is within the set. Maybe it is easier if I can show you the figure in the next. Here, this figure here represents a convex function. Okay, and this figure in here, in A, this is non-convex. In B, this is convex. You see, the convex function in 2D in here represent like circle, ellipse, something that close. Non-convex, you see, if you put a line of any point, any 2 points within the curve, the shaded curve here, you will see the line sometimes will go out of the curve. Okay, when you put the, okay, I will draw here. So if I put a line between these 2 points here, okay, the line is always within the shaded area, isn't it? If I put in the convex 2 points, any 2 points, and I draw a line, the line is always within, correct? Within the shaded area. But if I put a point in the non-convex here, okay, yes, if I put it in here, yes, it's within, but if I put it here, it's actually outside. The line is outside the shaded area. So that means if the line is outside the shaded area, that means it is non-convex. Now come back to the definition here. You see, I have 2 points, x and y. Okay, this is the x and this is the y. And t and 1 minus t here represent the what? The segment line, the line segment, right? So if you put this equation, that means you will have a line segment. So this definition means any line segment between 2 points must be within the S. Within the, so this formula, within the S, meaning within the set itself. If it is outside the set, that means this is non-convex. If it is always within the set, that means it is convex. Up to here, do you understand the definition of convex? Later on, you will see this definition of convex is very, very important. We can use this for any other purposes, you know. So, other definition of convex is also this one. A function fx is defined as a convex set omega. Yeah. It is convex if and only if it satisfies that the sum, if I put the input here, alpha x plus beta y, okay, the value of this is always less than if I put them separately. So in the graph, you see this, in this chord, you see the line AB, okay, is above the curve, okay, that any point P, in this case, would have the line within and always smaller. You see, the L alpha, which is alpha L, and L beta, which is beta times L, is always smaller. Okay. Oh, the total, this is the L alpha. This is the L beta. Okay. So the function here is always smaller. So meaning that it is always down. So the line is always up. Okay. This line is always up. So that's the meaning of convex. So we will stick to this formula here, okay, of definition of convex. Okay, up to here, any question? Are you still there? Hello.
I'm here, Mr. Yeah, I'm here. But no questions.
No question. Okay. If no question, we will continue with the next slide, which is linear programming. I know you have learned linear programming. I would like to review. Okay, so that's why only a short time we will review this. Okay. I think this is the choice. So I want to share with you the linear programming. There. You can follow this from the slide in Moodle, in Refolate the Moodle. Can you get it? Did you open?
Yeah, sir.
So
Okay. Okay. So by the end of this lesson, you should be able to learn about the step of LP and know how to use linear programming using Solver. Did you solve linear programming in the OR1 using Solver also?
No, we use manually.
Oh, you use manual? Really? Okay, good. So then you will use, do you have Excel with you?
Yes.
Yes.
Okay, open it, okay? Open the Excel. Okay, so what is linear programming? Linear programming, okay, if you have both constraint and objective function are linear function. How do I know it's linear? Linear function is simple, okay? So you will have a linear combination, which is something like this. Oops. Okay, so you will have A times x1 plus B times x2 plus C times x3 and so on. So this is called linear combination. So if you have linear combination, okay, both in constraint and objective function, then you have linear programming. Simple? So in OR1, you learn about simplex method, I believe, right? Is that so?
Yes.
Yes.
Mm-hmm.
So you know how to put your linear programming problem into a simplex table, correct?
Yes.
Okay, good. So I will not discuss simplex in that case, okay? So this is the usual, it's formulated in 1947 by Danzig, okay, to solve a problem during World War II, logistic problems. Okay, now is one of the major optimization problem. So this is the general linear program formula. We talked about it a while ago. Now, to guide, okay, these are the several questions that you will ask, okay, in creating linear programming. So first you need to find what is the objective that you want to optimize. Okay, next, what are the decisions that you want to control that would affect the objective. So the decision here, you will put them into variables. So we call this decision variables. And then what item dictate the constraints on the range of choices. That means you will have some constraints, and each constraint will have certain range of choice. Next, how are the value of the objective function related to the value of decision variables? Now you have the decision variables. Now you put the decision variables, usually we put x1, x2, x3, and so on, into the objective function. Okay, so number one, what are the objectives that we want to optimize? Meaning you need to know whether you want to maximize or you want to minimize. Number two, what decision you want to control? That means you need to define your decision variables. Number three, you need to define the constraint. Number four, you need to define your objective function, which relate the value of decision variables. Okay, and then number five, what decision provide us with the optimal value of the objective function? That means you already find the solution. The solution is the optimal value. Then you need to put back, okay, I get the solution with this, the value of the maximum or the minimum, and the value of the x of the decision variables, right? And number six, you need to find how sensitive is the optimal decision to the assumption made in the analysis. Are there alternative decisions providing satisfactory result with less sensitivity to this assumption? So it means you need to find the sensitivity analysis also. Okay, so the sensitivity analysis means you change the value of the decision variables either to the left or to the right, a little bit to the left, a little bit to the right, meaning a little bit up or down. Then whether it is sensitive or not. Okay, so you want to find a better way to get the result that is less sensitive. The goal is to find less sensitive. Okay. Now, solving optimization problems consists of two parts. Number one is to formulate the optimization problem. Okay. First, you identify the unknown variable. This is the decision variables. Second, you organize the data to include that unknown variable. Third, you identify the constraints of the unknown variable, and then you determine the objective function. So this is the steps, okay? The 4 steps that you need to follow. Next, after that you solve the optimization problem. This is easy. So first you transform the mathematical language into spreadsheet. After that, you solve using spreadsheet. So this is what we will do in this hour, okay? So I'll give you the well-known transportation distribution problem. So this is the common problem in transportation distribution or logistic. In this problem, you have a certain number of suppliers. And then you have also the certain number of outlets. Okay, so you have supply and you have demand. Okay, and then you want to transport from each supplier to its outlet. Okay, and to transport from supplier A to outlet A, or so it will have some costs, transport costs. The transport cost is generalized cost. What's the meaning of generalized cost? Generalized cost is either time, money, or distance, or the three of them. Okay, when we say cost in here, it's not necessarily money. It can be time, can be distance, can be money. So it's called generalized cost. Now, the problem in here is to find how many goods to be shipped between each pair of supplier and outlet, such that the total transport cost will be minimized. Okay, so for your practice, okay, here is the problem. Say a computer company has two warehouses, warehouse A and B, and two retail shop with this retail shop Y and Z. The warehouse A has 250 computers, warehouse B have 400 computers. This is representing the constraint. Now, retail shop Y need 300 computers, while shop Z needs 200 computers. You see, the total needs, the total demand in here is 300 plus 200, it is 500. The total supply is 400 plus 250, which is 650. It's not the same. Okay, the demand is not the same as the supply. And then the table here represents the shipment cost of a computer. Okay, now the question is, should the how much? Okay, the company transport the computer to minimize the cost. So come back to the optimization problem. First, you need to identify the unknown variable, isn't it? Second, you need to organize the data to include the unknown, and then to identify the constraint and determine the objective function. Let's do that, okay? So first, you identify the unknown variables. What do you want to know? We would like to know the number of shipments of computer from one warehouse to one retail outlet, correct? Now, since we have only two warehouses and two retail outlets, that means you need to have at least 4 unknown variables. So let's say because the warehouse is A, B, and the outlet is Y, Z, then you have 4 decision variable or unknown variable. In this case, X, A, Y, X, A, Z, X, B, Y, and X, B, Z, isn't it? So X represents the quantity of the number of computers to be shipped from warehouse I to retail outlet J. Until here, any question?
Oh, sir. No, it's clear.
Clear?
Clear.
Sure? So you know how to identify the unknown variables.
Yeah.
Okay. Next is to organize the data. So you see the data a while ago, the table. Now I put the variables here. So you have X, A, Y, X, A, Z, X, B, Y, and X, B, Z. So this is how you organize the data. Until here, okay?
Okay.
Okay, this is just the same as before. I just put the variables name here, right? Next. So next is to identify the constraint. You see the total supply from the warehouse cannot exceed capacity, right? So in that case, XAY plus XAZ less than or equal to 150. XBY plus XBZ is less than or equal 400. Because the total supply from the warehouse cannot exceed its capacity. Okay, come back to the table here. You see this is just the row, correct? So x, ay, az, that ay here, az here. So less than 250. xp, bc, less than 400. So in the, it for each warehouse cannot go beyond the capacity. Then the next constraint is that the total demand for each shop must also be accommodated. That comes from the each column in the table. You see, AY and BY is equal to 300. Okay.
Wait, sir. In this case, usually we have what we call with Z function, right? Z equals to blah, blah, blah. The one that we want to, in this case, I think this is the one that we want to minimize. So we will have also a function like Z equals to.
Correct. That one is objective function, right? That will be in the next step. Correct. Very good. That will be in the next step, okay? So now we start with the constraint first. Okay, we identify the constraint first. So you see the constraint here represent the row and the column, right? And then you have boundary constraint, which is all the constraint, all the decision variable must be positive. Okay, the next steps, this is what you just mentioned a while ago, right? This is the third step is to determine the objective function. So you decide the constraint first, and then you decide the objective function. The goal here is to minimize the total cost of transportation. So how do you get the total cost? Of course, you go to the table a while ago. The total cost is the unit cost, which is 18, okay, multiplied by the variables. Okay, 15 multiplied by the variable xaz, 12 multiplied by the variable, and then you sum all of this, right? Then you get the objective function here. Okay, up to here, any question? Is it clear?
Yes.
Super, yeah.
Yes. Clear.
You learned this in OR1 already, so this is like repeating, okay? Just a review. Then you have 4 variables, isn't it? So this is your optimization formula. So you minimize the Z subject to constraint all of this. Okay, this is your human. From the real world problem, from the word problem, now you need to create this LP formulation. This is the optimization formula. My question to you, can you do this on your own? Can you create this formulation on your own? You need to find the objective function and the constraint. Can you do it?
Yes.
Yes? Sure. Any question about that?
I don't think so.
Okay, very good. So then let's go. Okay, this is, if you use Minisync, you can just copy and paste and do it. Okay, if you don't, let's do it in Excel, okay? Okay. This chart annotation. Okay, let's do it in Excel. I want you to do in Excel. Okay, so here in Excel, can you see it in Excel? Now you type the variables. You have 4 variables here, and you can type any numbers. Okay, you can type 0, 0, 0, no problem here, or 1, 1, 1. Can you type similar like this? So all the variables here, you put any numbers. The one in yellow is any numbers. And then now you set up the constraint. You type the constraint here. Okay. And the constraint is x AY plus XAZ. So you just get that. You know how to use Excel, isn't it?
Yeah, but not all.
Just typing. Can you just type?
Okay.
And then you also type later on the objective function. Okay, so you have the cost, you type again 18, 15, 12, 14 there. And then the objective function, you multiply each of these variables with the cost. So can you do it? And then can you share your screen to me, each of you, when I call you? Is that okay?
No, I ain't got any Excel on me now.
Okay. So open your Excel, do exactly what I did a while ago. And then now you can share your screen to me. Anyone ready? Want to show? Share your screen. We'll do something like this. Is there any difficulty?
Still type picture.
Okay, you type.
Wait.
So once you finish, you can share your screen.
Hello.
Yes.
For the 15 and the 14 and the 15, why did you put only equal, not less than equal?
Oh, in the problem,
The 14 and the 15.
yes, in the problem that we have, right? We said that the retailers need 300. So the capacity is less than, because the total demand is not equal to the total supply. So one of them must be less than. You can also put equal or less than equal. That's okay.
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 Thank you.
But in the problem that we have, we put the total demand must be the same as total supply. So in that case, we put equal so that it will go to the constraint value. If everything is less than, so there is possibility it will go less than the value, right? Remember, the total demand is not the same as total supply in this case. So here it is. A while ago, you see, when you identify the constraint, right? So here we put the total demand is equal, not less than equal.
Oh, okay.
Correct? And your question is valid. Why it is equal rather than less than? Again, the answer is because you want to have one of them must be straight to the constraint itself, because the total supply is not the same as total demand. Now you put that into Excel. So here it is. So what you need to do, the one in yellow, in this case, is the one that you type. The one in other color, for example, orange and blue here, is the one that represents the formula. Okay. So especially the objective function must represent the formula that you have. So this is how you do in Excel. Are you done?
Not yet.
Not yet, okay. You make it first because otherwise we cannot solve this.
Wait, do you have the answer?
The answer?
Yeah.
Answer, okay. You need to have a solver here. Do you have solver?
Yes, I do have solver.
You have solver?
Yep.
Then if you have solver, then you put the solver parameter. Set objective is the objective function, which is C22 in my case. I want to minimize, and then by changing the variables, what variables in this case is the decision variables, right? This one. Okay. And then you type all the constraint. Okay. So in this case, C9 must be larger than E. Way larger than. Oh.
Yeah.
E90.
I got 0. I have
Hello?
0.
I think your sign is reverse.
Yeah, I think my sign is reversed. Like
C9 bigger than
C9. What is C?
Isn't it supposed to be C9 smaller or equal?
Correct. C9 must be larger than 0. E19 is 0. Is correct. This is correct. C9 in here is the XBZ must be larger than 0. Right. This is the boundary constraint. Then C13 is this one, the total of xby and xbz must be less than E13. Okay, so you add all the constraint here. Basically, the LP formulation, the optimization formula, you put it into the constraint here. Once you do that, and then you just click solve. Okay, then you get the answer.
Oh, I mistyped the question.
Okay, so you found the solution. Then you, of course, this is 0, right? It's basically 0. Okay, so again, you use the solver, you solve it, and the sensitivity analysis, you just type the sensitivity analysis, and you will get the report of sensitivity analysis. Okay, so yeah, solving is easy. Okay, once you put into formula, you just type it and then put into Excel and use Excel solver. Just click one button, you get it all. Right?
Yeah, I got it.
Okay. So if you don't have solver, then you go to the account or options in add-ins and manage, and then you click the Excel solver add-ins here.
Sorry, can I see what the cell reference? What the constraint like the?
This one?
Oh yeah. Good.
Okay.
So the objective is the set, right?
The C is the objective, right? The objective in this case C22 with the Z.
Okay.
Your goal is to minimize. Right? Variable cell is the variable cell there, C6 to C9.
Okay.
And then the constraint you put one by one. One by one is exactly the same as the LP formulation, the optimization formula.
Oh.
So now if you look at the method of solving here, you can use either nonlinear programming, simplex linear programming, or evolutionary. Evolutionary here represent the genetic algorithm. Simplex is the one that you learn in OR1. Okay, nonlinear is the one that we use right now. You can also change the option, but actually you don't need it. Okay, if you use GA, you can change the evolutionary mutation rate, population size, and so on. The same thing here. This is GRG is basically Newton method. Okay, conjugate gradient. Anyway, so you don't need to change this. So you know how to solve linear programming, you know how to solve a transportation problem. Okay, we use Excel and you know how to do it. In fact, you can see if you want to add the constraint there, You can also use binary, integer, difference, right? So that means you can also solve integer programming like traveling salesman problem, Chinese postman problem using Excel.
Oh,
Okay. Interesting.
Okay,
okay.
now interesting.
Okay.
Okay, I see
Okay.
the power of Excel.
Okay, now it's better, right? You like Excel better.
Yeah.
Yeah, okay.
Mhm.
So, okay, depending on how you define the constraint here, you see integer or binary or difference. Here, that represent the integer programming. See, now everything becomes simple as long as you know how to make the real world problem, okay, into the optimization formula, correct?
The
Once,
objective function, yeah.
yes, the objective and the constraint function. Once you make that, everything is so simple. Okay, it's just typing, just inputting into the computer. It's
I
just
see.
a few
Okay.
minute job. Okay. OR1, you did not use Excel. That's strange. How do it?
So we were taught manually.
Yeah, that's important to know manually. After that,
After that,
We like the lecturer said that
Master though.
the lecturer said that it is possible using Excel, but he said that during the OR1 he wanted us to use manually. Then, but he also taught us how to use the Excel a bit, just like at the beginning of the course, and then at the after he explained that we can do this using Excel, he specifically asked that in his course we use the
manually. Yeah, I think that's good course. That's if I teach that, probably I will do the same.
okay.
Okay, so now you know how to solve everything using Excel. So again, this is just a review. You have learned all of this in OR1. Okay, so this is just a review. So did you solve it? Did you get the same result with me?
Yeah, I did.
To share your screen. Who did it? Abel, did you finish?
Oh, yes, I did finish it.
I'll share your screen.
Okay, hold on. There we go.
Oh, you get it. Okay. Yeah, very good. Good. Michael, did you finish?
yeah, but I got different.
Oh, why?
I got 7,400. But wait.
Share your screen so that we can see.
Okay. Wait. This one.
Oh, that's strange.
I think I got. Abel didn't include this part, right? For the fourth one. I think I got error in that part, but I will try it again.
Wait.
Yeah. I don't know. You didn't include this four part, right, Abel?
But the lecture, Mr.
Yeah, I include that part.
He
Yeah.
included it, but it's the same with me.
Yeah. So maybe I got an error. I don't know. This is the sulfur part.
Oh, okay. So I think because you put mix unconstrained variable here. If you unclick that.
Oh, what? Oh, this one.
Try to solve.
Oh, I see.
Did not find the possible solution because you did not include the boundary condition. Can you include the boundary condition that XAY must be larger than 0, right? XA
Yeah.
must be larger than
Oh, larger.
larger.
This one is
Yeah,
larger. Oh, wait. Oh.
C3, you need to add another constraint. C3 larger than 0. That one, larger than equal to 0. 0. And then C4 larger than equal to 0. Again, add. And then C5 again, larger than 0. Again, and then last time, larger than. And then OK. No, you cannot empty cancel.
Yeah.
Okay, so solve it. Not valid. Oh, something is still wrong. What is your formula?
You can remove your previous wrong constraint, Rodney. You still have
The solver, you should use linear.
You should use.
Oh, the
Linear.
simplex one.
Oh, simplex. Oh, not the non-linear.
You can use both. Actually, the three of them will not give you different.
Oh.
I think something is with your formula of.
Yeah.
Of constraint probably.
Okay.
Okay, so.
Okay.
Again, you know the answer, right? It's in the slide. So you try it again.
Yeah, I will try it again.
Just want to try. Linian, can you share your screen? Did you get it?
Mine's also an error. I don't know why.
Oh no, I haven't got it. I got confused in the middle.
Okay,
Wait,
show your screen, Lilian.
Oh. But I think, wait. I tried to use the different method and I got wrong.
Okay, you can experiment, of course. So, yes. Your objective is very big.
Yes, that's why I got confused.
Something. What is the meaning of usage in here?
It's like the A, like this is like A. I think there's something wrong with the variable. I think I misput the variable.
Okay, so try to do it. Okay, so can I give you assignment for this so that you will all do it?
Okay.
Sure.
Okay, so it's just anyway. You try to do it with the correct one. You get the real answer. Right?
Okay. Yeah.
Okay. So again, the next one in the slide I will show you. Okay, so the alternative solution is if you have actually, you see the total demand is actually dependent on it added to the constraint, right? So instead of 4 variables, you can also make it into 2 unknown variables because you put it equal, right? So that means xby is equal to 300 minus xay. In that case, you can reduce the constraint. Okay, become something like this. And based on that, now you can reformulate the constraint into 2 variables. And again, you can solve it. You can determine the new objective function. And when you solve it, you will get a different objective function, but the result will be the same. Okay? The result will be the same. Anyway. So x, a, y is 300. Right? So you will get a different result, but eventually when you want to get it, you will get exactly the same result. Here I get this value, 300 and 100. Let me share the screen for that. So here I use two variables. So again, I get this result. So I hope you can try. You submit it up to next week, your assignment. Is it okay?
Yeah.
Okay. 2 variables and 4 variables.
Okay.
Okay. Just use, what you will submit is just an Excel file. Is that okay?
Okay.
On the Revolut, right?
Yeah, in Moodle, in Revolut.
Okay. Okay.
Okay. Good. So I think we passed the time already. So thank you for today. I hope you enjoy the class.
Okay,
Okay.
thank you, sir.
Okay.
Thank you, sir.
Okay, thank you, sir.
So see you
Thank
next
you, sir.
Okay.
See you.
See you next week.
Please read before the class. Then next week we will discuss about decision making, right?
Yeah.
Okay.
Okay. So please read the slide. Okay.
Okay. Thank you.
Okay.
Thank you, sir.
Thank you. See you, sir.
See you.
Thank you.
Thank you. See you, sir.
Okay. See you.